Hello everyone and welcome back to our Applied Cryptology course. This week we continue with randomness in cryptography. So far we talk about a lot of different cryptographic algorithms, and we use the word random a lot of times because we said that whenever we generate a parameter, whenever we generate a key and so on, we always insist on saying that it should be random. But the question is, how can you determine that something is random? So randomness in cryptography is really important because sometimes attackers does not break the crypto system, but they use the weakness in the randomness when the key is generated and so on. So we will see a few examples in a minute. So let's first start with some areas where we need randomness in cryptography. So cryptographic algorithms require random numbers for parameters like key streams of one-time path. So when you generate a one-time path, we said that it has to be random. So it is not an easy task to generate a very long sequence of zeros and ones that are random. Moreover, secret keys of a symmetric cipher system should be random. Of course, in a public key cryptography, this secret key also should be random, but we haven't seen public key cryptography yet, so this is why I'm talking about symmetric cryptographic algorithms. Like in all of the block ciphers, stream ciphers, or authenticated encryption algorithms we have seen so far, we use secret keys like 128 bits to 256 bits and so on. They have to be random. So the question is, how can you generate it in a random way? Because as you know, we are using secret keys because we are performing encrypted communication whenever we surf the web, but we never use these keys ourselves. So the operating system, the browser, generates the secret keys for us. So we have to be sure that they are generating them in a random way. So this is one area that we need this randomness. But you may also recall that we talk about password-based key derivation algorithms, where we choose a password and we take the hash of it like 10,000 times, and the output of the hash function is regarded as a secret key. Here we can be sure that it is random, but of course then the attacker may try all of the passwords and so on. So other than password-based key derivations where you have the control, most of the time you don't have the control and the keys are generated by the operating system, browser, and so on. Yes, so the public key parameter should also be random. We have examples where you can put backdoors when you choose these parameters in a specific way, which is an example when we will be talking about dual elliptic or random number generator, where the random number generator had a backdoor actually due to these selected parameters. Of course, session keys should be random, nonces should be random, initialization vector should be random, solve should be random, and so on and so forth. So in almost every cryptographic algorithm you use, there has to be a random number generator so that you can provide full security for your system. So now we understood that we need randomness. Let's talk about some definitions and then we will talk about how we can construct random number generators. A random number generator, an RNG, produces a sequence of numbers on an interval minimum to max. We want an RNG to have the following properties: statistical independence, uniform distribution, unpredictability. Cryptographic algorithms mostly require random bits because we most of the time work on bits. So in other words, we choose minimum as 0 and maximum as 1. So you are producing integers. So most of the time, instead of random number generators, we will be talking about random bit generators, which is also can be converted to a random number generator because you can group the bits and convert them into numbers and so on and so forth. So first talk about statistical independence. We said that a random number generator should be statistically independent. This means that for a given generated sequence of values, a particular value should not be more likely to appear next. So it doesn't matter which. So this means that you have a random number generator. You push a button and it produces zeros and ones, and you stop it at some point. You look at all the generated zeros and ones, and by looking at it, you shouldn't have any advantage of saying that the next bit should be 0 or 1 with probability more than 1/2. Okay, so it should be statistically independent. The next generated value, the next value that is going to be generated should be independent from all of the previous ones. So I'm saying that, for instance, you use the random number generator, and just for some reason it produces 100 ones consecutively, but still it doesn't give any information to you about what is going to be next. Uniform distribution. All numbers are equally liked and none appear more frequently within the output. So this means that actually if you generate a sequence that is infinitely long, then all of the numbers that can be produced are appear with same number of times actually. So actually this will be used in frequency test, and so we will talk about it. Third one is unpredictability. An attacker should not be able to guess some or all of the values in a generated sequence. We can actually divide this notion into two. First one is forward prediction. Knowledge of previously generated sequences should not provide advantage to attacker when guessing the future values. Backtracking. Knowledge of some generated sequences should not provide advantage to the attacker when guessing the earlier generated sequences. So these are important because backtracking especially might be a problem if it is possible. For instance, you are using a random number generator for your to use in as a secret key for your block cipher, for instance. So if you are using AES and you generate all your keys using a random number generator, and at some point the attacker somehow captures the internal value of this random number generator. So this means that if he knows the inside value, he can produce the future values that you are going to produce. So this is forward prediction. But if they can go back just by looking at the value you generated, if they can guess what you produced before, this is backward tracking, and this way they can capture the previous secret keys that you use, and this way they can decrypt all of your previous communication. So let's talk about generating random numbers. Generating random numbers with the desired properties is difficult because computer systems are deterministic. That is one of the problems. A computer is a deterministic system. So saying to a computer to generate a random number actually is like asking an artificial intelligence what is their favorite number, because they have to guess somehow. So, but since they don't have, a computer doesn't have is not like a human, they cannot work in an indeterministic way, let's say. So sampling the seconds value from the system clock is a common approach for random number generation, but it cannot be used for cryptographic purposes. So this is a very common practice. You need a random value. For instance, especially in databases, when you want to add a new value to a table, you prefer some column to be unique. So this is most of the time by using the seconds value that is taken from the system clock. But this is not, of course, random when we say, if you consider the previous definitions. But moreover, if you are using this approach, there is a limited number of seconds that you can choose in a time interval. So the attacker can try all of those seconds values, which is not that much. For instance, if I'm not mistaken, in a year we have 2 to the 25, around 2 to the 25 seconds. So if you're using your secret key as a seconds value, then the attacker can try at most 2 to the 25 values and capture your key. So this is out of the question, never think about it. But unfortunately, people still use seconds value as a secret parameter or secret key. Using time between the user's keystrokes or mouse movements for an entropy source also do not provide the desired properties. So this is a better approach than using the seconds value that's taken from the system clock. But still, probably you're familiar with some applications or operating systems where they ask you to move your mouse on the screen for some time, and they capture data from your movements, and this way they generate actually some zeros and ones. It is a good approach, but it is not random, because most of the time you just shake the mouse and produce similar values. But still, it is better than using the seconds value. So in order to talk about randomness, we have to talk about entropy. So a measure of the disorder or randomness in a closed system is called entropy. The entropy of uncertainty of a random variable x with probabilities p1 to pn is defined as hx, which is the summation of the probabilities multiplied by their logarithms, and it is all summed up with a minus sign at the beginning. So of course, there can be different definitions for entropy, and I think this is referred to as Shannon entropy. So think about this as an example. Let's think about tossing a fair coin. So it can be either heads or tails. So we have, for instance, P1, which is 1/2, which is the probability of seeing heads, and we have P2, which is the probability of observing tails, which is also 1/2, and that's all. And in our example is 2 in this case. We have 2 possibilities, heads or tails. So if you compute the entropy of this random variable, it is 1/2 multiplied by the logarithm of logarithm of 1/2 to the base 2, which is, I think, -1. So you sum 2 values which are -1/2, -1/2, which is -1, and you have a minus sign at the beginning, and the result is 1. So please use some pen and paper to check the calculations I made in my mind. But this means that tossing a fair coin as a random variable has entropy 1. So this is actually a different definition for the information, because this means that a 1-bit value, which can be either 0 or 1 with probability 1/2, has actually entropy 1. So this means that it has at most 1 bit of information. So it can carry at most 1 bit information. So that is actually one way of looking at the entropy. So if you generate a random sequence of bits of length 100, if the probabilities are 1/2, then the entropy of that sequence should be 100 in this scenario. So this is actually, of course, when you divide it, it will be 1. I mean, in the best case scenario, you would get 1. So idea is to check what is the entropy of this system between 0 and 1. So if it gets close to 1, this means that there are more disorder in the system, so it is more random. But if it is close to 0, then this means that the entropy is really small. So this also means that it can be easily guessed, and so it is not random.